Notacon.
My name is Jim. For any of you who don't know me, I guess there's a couple of people that might. And this is just photography hour 2. Any of you sat through Amish's hour 1? Hopefully this is redundant, and hopefully everybody gets to learn something. So, presentation here was created under the influence of gin, and a lot of the test photography was as well. So once again, I can't apologize. And I might be drunk right now. This is most of the stuff we're going to talk about. So if anybody here understands all of this already, you should leave because it's going to get boring. But we're going to talk about some sensors, sensors in the bus, including film, everybody's favorite, raw files, a little bit of EXIF, and some exposure stuff, including unfucking up your pictures. A little bit of GIMP versus Photoshop. I am partial. And some post-processing demos, including white balance correction, some crazy stuff like fake cross-processing and distortion correction, some other stuff, and if we have some time, some extra credit stuff. So I guess we can begin. So I actually drew all this stuff myself, even though I did steal all the ideas for the images from everybody's favorite dpreview.com, which I highly recommend. So most people have sort of some understanding of how 35mm film works. Basically, light hits the film and it passes through various emulsion layers, an RGB layer, obviously, or an R layer, a green layer, and a red layer. That didn't make any sense. Sorry. And the light affects the chemicals and produces an image, and of course that just gets sent over to the roll of 35mm film. In the digital paradigm, there's kind of two different types of sensors that exist now. There's the standard color filter array, which probably most people have in their cameras. This includes CCDs and CMOS sensors. There is an exotic type of sensor known as a fovean sensor that really only is found in some Sigma cameras, and I've never seen one, so as far as I know, they don't actually exist. But basically, the way it works is, light will hit the sensor, and in the case of a color filter array, it'll hit either a green pixel, a blue pixel, or a red pixel. And but the problem with this is that, as most of you know, an RGB image will not have individual red, green, or blue pixels. They have just a color pixel, and so the image processor needs to sort of interpolate the color of an individual pixel based on 4 photo sites of a regular, of like a CCD or a CMOS sensor. This is what makes a fovean sensor somewhat better than a standard color filter array sensor, because a fovean sensor will actually produce an actual color pixel and won't have to interpolate anything. And so it has the potential to produce cleaner and sharper images. But like I said, it is exotic, and the technology is still being developed, but it's something that we all look forward to. Now, there are some advantages to the way film works. Perhaps most notably, the flexibility that it affords in terms of changing the type of film you have in your camera. Now, if you put like a roll of 200 ISO speed film in your camera, you have to burn that up, effectively before you can change the roll of film. I mean, obviously you can just pull it out, but you got the film in your camera. But at the same time, you could put IR film in the camera. You could put like something crazy like ISO 3200 in your camera, or ISO 50. You can always change the type of film you have in your camera. But when you buy a digital camera, you just have a sensor, and you don't really have a lot of latitude in terms of how the sensor gathers light, what it does with the light, and how it reacts to the light. But that's sort of the magic of post-processing, which we'll talk about in a little bit. Let's see. So, okay. This is kind of a very abstracted version of how data works in your camera, and I did make all this in PowerPoint, so it's kind of silly looking, and I beg your pardon. So you start with an image, you take a picture of a scene, and the light travels through optical elements and hits the sensor. All cameras work the same in this regard. Whether you're talking about a pinhole camera, a film camera, a digital camera, basically anything. It's all light traveling through optical elements and hitting some kind of sensor, whether it's film, whether it's a digital sensor, it doesn't really matter. Where am I here? With a digital camera, the light's going to hit the sensor, and as we saw previously, depending on the kind of sensor you have, it's going to hit a particular type of photosite. After it hits the photosite, it travels to an analog to digital converter, which I'll talk about a little bit more in a little bit. But the analog to digital converter basically produces a bunch of bits that end up as data, which eventually ends up, after it passes through the image processors, as an image. And as is probably demonstrated here with my image, the first one is not really anything like the second one. And of course the reason for that is because no matter what you do, the image that you end up with is never going to be the same as the image that you started with. There's a number of reasons for this, including dynamic range and color space, which I will talk about in a little bit. But suffice it to say, it's always an abstraction. And unfortunately, there's no real way to get away from that, but there are things you can do to try to get closer to reality, if that's, you know, what you want to do with your photography. All right. So, I'm not an electrical engineer, so this is correct. If anybody is, please let me know. But basically, what happens with a digital to analog converter is data is going to get passed from the sensor, data as light that ends up as an electrical current. And this is a very simple kind of demonstration of just like a 4-bit digital to analog converter. Most digital to analog converters that you'll find in your cameras are going to be like 8 bits, 10, 12, something like that. So the signal is going to come in from the sensor, and it's going to come in as a wave, or not necessarily as a wave, but at least as a series of electrical current. It hits the digital to analog converter, and the digital to analog converter assigns a value based on the strength of the current that it's receiving. So in this case, you'd end up with like a 4-bit file, just in this simple example. But like I said, a lot of digital to analog converters will be, you know, between 10 and 12 bits, sometimes just as few as 8. But the digital to analog converter is what is responsible for dynamic range. And dynamic range is kind of a buzzword of digital photography that not a lot of people completely understand. It has to do with the variation between the darkest pixels in an image and the lightest pixels in an image. And you'll see this in pictures where, like for instance, if you're standing inside of a building, inside of a house, and you're taking a picture and the window, like in the background, is just pure white, that's a limitation of dynamic range, because what's happening is the values of the amount of light coming in from the window is too bright compared to the rest of the scene, and the window's getting blown out. Like there's just too much there. And it's not like a contrast problem, it's a problem with the sensor being able to balance between the darkest parts of the scene and the lightest parts of the scene. Some of this can be compensated for with things like metering properly, but when it comes down to it, between the sensor and the analog to digital converter, they're just not able to keep up with the amount of variation in the scene that's coming through. In fact, the human eye even has the same sort of limitations, where if you're looking straight at the sun, you're not going to be able to see anything but just pure white. And it's sort of the same thing. In fact, it is exactly the same thing. It's a dynamic range problem. Although I should say that it's been said that the human eye is capable of something on the order of 25 to 30 stops of dynamic range. And as a point of comparison, like a high-end film, like Velvia film, for instance, might be good for up to 10 to 12 stops of dynamic range. Like probably the best digital camera that you could buy today, which would probably be like a Canon 1D Mark II, is rated at something like 9 stops of dynamic range. So you can see that we have a long way to go before we can match the power of the human eye, but or even some high-end films for that matter. But you can see like kind of how fundamental it is to photographing a complete scene when there's a lot of variation between light and dark. So, but another part of that has to do with the color space that's involved. And I wonder, all right, here we go. Oh, that's crazy. Color space is how the data that your camera produces is interpreted as color, because the data that your camera produces is really just a series of bits. It's not color information. It's not an image. It's just a bunch of bits. In your machine, and whatever you're using to display it, whether it's a computer displaying to a monitor or a computer outputting to a printer, it needs to be able to describe objectively what that information means in terms of color. And so color space is sort of just a way of describing mathematically within a range what a particular bit value means. So in this case, we can show an example here of just sort of like a kind of a light orange, and what that means in terms of RGB. This is of course just an 8-bit value, and it is arbitrary. But in any case, lab color, which might also be called CIE lab, is sort of a theoretical color model that is said to describe the range of human vision. And as you can see, all of our artificial color spaces are invariably a lot smaller than that. For instance, CMYK, which is what pretty much everybody uses to print anything. Like any magazine you ever pick up is going to be printed in CMYK. And as you can see, it's a lot smaller than what the human eye is capable of seeing. ARGB, or Adobe RGB, is a color space that a lot of high-end digital cameras are able to create files in, which is bigger than CMYK or sRGB, but at the same time it's still a lot smaller than what the human eye is capable of seeing. sRGB is kind of significant because it's what most cameras are going to default to, and it's also what most normal computer monitors are going to be capable of displaying at. There are some crazy expensive ARGB monitors, but most human beings don't have them, so it's kind of irrelevant. But what's interesting about that is that you might be able to take pictures in ARGB, or even some other sort of strange exotic color spaces that exist, but you're not really going to be able to see them on your monitor. Which is to say that if you go to edit them on your machine, you're not going to be seeing all the colors that are actually in there. Now, of course, there are ways to downsample. There are ways to sort of approximate between two different color spaces. But if you're looking at an ARGB file on an sRGB monitor, you're not seeing everything, which means that when you make changes, you're going to be making changes to parts of the image and colors of the images that you're not actually seeing. So it can be kind of tricky in that regard. That being said, if your camera is capable of taking pictures in ARGB, I do recommend it. You end up with a file that ends up capturing more colors than if you just took it in sRGB, and it's usually better to downsample later than just limit the number and the amount of colors that you're taking in the first place. But we're going to talk about this a little bit more in a minute too. I want to talk a little bit about raw files, and I like sushi as well. Raw files, if your camera is capable of producing them, and most cameras these days are, but a raw file is basically a direct dump of the data that your sensor gathers straight to a file with no interpretation, with no correction, no compression, nothing. It's just all the data that your sensor gathers all at once in one big huge file. This is usually a good idea to do if you're interested in post-processing later, but it has an additional advantage in that most raw files will be higher than 8 bits, because if you have a sensor and a digital to analog or I should say analog to digital converter that operates in more than 8 bits, for instance like a 10-bit or a 12-bit analog to digital converter, you're going to end up with a 10 or 12-bit raw file, which is going to have more